Okay, so now we're ready for the third installment of application of classifications. Bhishan, take it away.
All right. So today I'm going to start off by telling you about the UCT. So this is something very intrinsically related to KK theory, which I'm not going to get into. I'll just very briefly say something, and then I'll tell you the kind of T-star algebras that satisfy the UCT. So first of all, let's say that separable C-star algebra A is in the UCT class, denoted N. So the way I'm going to describe this to you is not exactly how it's phrased in the original Rosenberg-Schocket paper. The description I'm going to use is sort of equivalent relation due to Scandalis. But I'll comment on the Rosenberg-Schocket notion shortly. So UCT class N, if it's KK equivalent to an abelian C-star algebra, if exists some locally compact space X such that A is KK equivalent to C0 of X. Okay, so here, as I said, so KK is Kasparov's bivariant K theory. And what I'll say, you know about this or you don't, so all I'll say is that it encapsulates both K theory and K homology as special cases. So, which includes K theory. So K theory of C-star algebra A that has to do with finally generated projective A modules. So I always have to remind myself which way around it goes. So I think you want A here and complex numbers here. So K theory is KK complex numbers this and K homology. KKAB is the structure is you want B modules with some sort of A action. AK. Okay, as special cases. All right. This is what you might call the UCT class. The class of C-star algebras that is studied by Rosenberg and Schocket is what is referred to as the bootstrap class. And in their paper, they refer specifically to nuclear C-star algebras in their bootstrap class. So let me tell you what this bootstrap class is. The bootstrap class is N-nuc. So these are the nuclear C-star algebras in N. A in N such that A is nuclear. And it's constructed this way. So these C-star algebras, it's called the bootstrap class because it's described by some initial data, if you like, and some rules for building out. So this. I mean, I don't think this is what they had. I don't know if this is what they had in mind, but there's this notion of bootstrapping in computer programming. You start with some initial data and there's some rules, and you build up from there. So the rules for building up C-star algebras in this bootstrap class. First of all, the complex numbers.
So there's a question.
Yeah.
So KK equivalence means the
yes.
functors is.
Yes, I didn't say what KK equivalence meant. KK equivalence means that there is an invertible element in KKAB. So in KKA C0X, there is an invertible element, which is invertible with respect to this Kasparov product. Right, so maybe I should write this down. So,
It's okay to grade it or not?
yes, it is.
It is.
Yeah. So, okay, maybe I will, where should I write this? Maybe here. So, A is KK equivalent B if there exists an irreducible element in KK AB. Okay, so there's some X. So what this means is there is some Y in KKBA. Such that if I do the product, we discuss bar product, X times Y, this will live in KKAA, and this should be the class of the identity function.
Seems in KK0 then.
Yes, yeah, okay. At the moment, eventually it will be.
There are some invertible elements in KK1.
Yes, if eventually I will talk about it with a grading. At the moment, no grading. So at the moment, just so X times Y is the class of identity A. No, I get this the right way around. X times yes, and then Y times X is the class of identity of B. Okay, but what I will say shortly is that in the UCT class, KK equivalence just means isomorphic K theory, actually. Okay, right. So the bootstrap class, first of all, the complex numbers is in it. It's closed under sequential inductive limits.
Have you introduced the Kasparov product?
No. And I said I'm not going to. I don't want to talk about KK theory at all. So I'll just tell you how it relates to K theory, and that's it, because we will be here all month if I have to tell you about KK theory. So N nuke is closed under sequential inductive limits. It's closed under extensions. In fact, even more is true. So if two algebras in a short exact sequence, let's say 0.
Sorry, can you say again, what is this? Currently N without subscript?
Just the algebras that are KK equivalent to abelian C-star algebras.
Okay.
And with the subscript, it's just the nuclear ones.
Yeah. Thank you so much.
So if two algebras in a short exact sequence are an N-nuke, then so is the third. And lastly, it's closed under KK equivalence. In particular, it's closed under Morita equivalence. KK equivalence. Hence, Morita equivalence. Right. From these basic defining properties, you can deduce that a variety of other C-star algebras are in this bootstrap class. So in particular, I'll write this down in a second. So in particular, all of these inductive limits that I described on Monday, these ASH algebras, which were things like the built out of blocks, which are things like continuous functions from some space X into matrix algebras, maybe taking subalgebras. All of these will lie in the UCT class, will automatically. All right. So let me mention. Okay, let me write this down now. So the kinds of algebras that NUke contains. NUke contains all abelian algebras. Caesar X from X. It contains limits of type 1 algebras, what I was just describing. So type 1 means it's a statement about the kinds of irreducible representations you have. they generate type 1 Polynomial algebra. So the things where the irreducible representations such as into matrix algebras, for example. So these, so type 1, an example would be, as I said,
If you mean direct limits, co-limits.
direct limits. I always when I mean inductive limits. So yes, co-limits. So e.g. so things like this, or subalgebras. And it's closed, and is closed under tensor products. So it's I'm speaking about nuclear C3 algebras. Any tensor product, it gives the same thing. So the minimal tensor product, say, and cross products. In certain cases, so for G, the integers or the real line, it's, I believe, open, whether it's closed on the cross products by circle or even finite cyclic groups. This is not known. So open or G circle.
It's not the question of being abelian. So what makes Z and R so special?
Yeah, it's a good.
The contracting duals are one-dimensional.
Let's say that's. I don't know. I mean, I'm off the top of my head. I can't remember. I can't remember how one shows that what I claimed is true is true. In fact, there's a very general result by 2 that any amenable group void, the C-star amenable group void, satisfies the UCT.
But your remark was not so completely funny because when you have Z and R, well, the contracting duals are compact, which is not the case for circle, for instance. But then Zn is self-dual.
Yes, absolutely. Yeah,
but look, this product with that, it's something like adding one topological dimension.
Yeah, okay, sure.
So if you are adding classical dimensions, it's closed with respect to this. Okay.
Why isn't circle adding a classical dimension?
Sorry?
So why isn't the circle adding a classical dimension?
Circle and the line.
Open for G equal to torus. That's my point, but it's true for R, not true for the circle.
Yes, I mean, we can speculate for abstract reasons why this should be. I mean, I don't know.
Cyclic group is.
You have the word open.
All right. So all of the C-star algebras that we encounter realistically in the classification program say they satisfy the UCT. Automatically, what I mean is the models we have for classifiable C-star algebras, the UCT is apparent. But still, we need to include it as an assumption in general. All right, so let me now describe to you this Rosenberg-Schocket theorem.
The group C-star algebra of non-stable groups, can they be in UCT class?
That does satisfy the UCT, yes. You see, yours, yes. Yeah, I'm not sure what the I'm not sure how generally it is true that a group C-star algebra automatically satisfies the UCT. Yes. I mean, any C-star algebra you can reasonably construct will satisfy the UCT. So I will mention the UCT problem shortly. Maybe I'll just mention it here.
Would be an example that open algebra that does not.
Okay, yeah. So let's address this now. So the UCT problem is n-nuke this collection of all nuclear C-star algebras. So yeah, n-nuke equals set of all nuclear.
Yeah.
Open problem, one of the major open problems in operator algebras at the moment. If we were to ask, this not n-nuke, but n, the algebras that are KK equivalent to abelian C-star algebras, is that every C-star algebra, that the answer is no. And there's this example that I mentioned last time by Skandalis. So you take this kind of lattice in this group of quaternion isometries, and you take the reduced group C-star algebra. This does not satisfy the UCT. I believe this, so this would be a non-nuclear C-star algebra, it would be a non-amenable group, but I believe it is exact. I mean, I think you need to do quite a bit more work to get a non-exact group C-star algebra, right? So, but it's open, not known whether every nuclear C-star algebra automatically is in this class. Okay, right. So usually, I mean, originally, when people say that the UCT, it's described in terms of this exact sequence, which I will describe to you now. So the theorem, okay, so Rosenberg and Schoppitz, they show that this sequence falls throughout the bootstrap class, and Skandalis's observation was that being in the bootstrap class is equivalent to being KK equivalent to an abelian C-star algebra. So I'll also mention Skandalis, because that's how I defined this class. So A is KK equivalent to an abelian C-star algebra if and only if for every separable C-star algebra B. There is a short exact sequence. All right, so 0, it's going to relate the KK AB to the group of homomorphisms between the K theory of A and the K theory of B, and that would be an isomorphism modulo torsion, essentially. So modulo this derived functor of the Hom functor. So X. Yes, you're right. I misspoke. Maybe I'll write this like this: K star plus 1B goes to KK AB goes to K star A, K star B. 0. All right. Well, what I mean here is that this map is degree 1, and this map is degree 0. So this KK is Z2 graded. There's a KK0 and a KK1. So this maps the even grading to the odd grading component and the other way around, and this just preserves the grading, these maps. All right, and
KK is KK0.
no, I mean, no, I mean, there, so KK0 would, okay, sorry, yes, I should have a star, sorry. Yeah, I should have, I mean, KK0 gets mapped upon K0A to K0B, direct sum K1.
But
K1,
then what is on the right hand side?
Hom of K star A, K star B. So what I mean is KK0 gets sent.
On one.
What I mean is that
Degree 1. What's degree 1?
what I mean is this. So K0 is B, direct sum K1A, K1B.
But then it, yeah, but from KK1.
KK1 will go to K0, K1,
K1.
K1, K0. Yes. This was. Okay.
Yeah.
Okay. Fine. And this, there is actually a splitting map, but it's not a natural splitting map. So unnatural split. Supernatural. All right. So modulo this X group, KK is, it corresponds to this homomorphism between K theory. So in fact, if either, so this will just be 0 if, for example, K star A is torsion free or K star B is divisible. maybe I write this down. So, in particular, KK, AB, KK star is isomorphic to A star A, A star B. If, for example, A star A is torsion free, or K star B is divisible. Okay, yes, I think it's okay. And also in this class, any invertible element in here corresponds to an isomorphism in between K theory. So if A and B are both in the UCT class, then being KK equivalent just means that they have the same K theory. Okay, so I mentioned the UCT problem. I mentioned that outside of the nuclear setting, it's known there are C-star algebras that do not satisfy the UCT. What I will just now briefly mention is how the UCT often appears in classification. One of the ways is, so relatedly, algebras in this class, or actually I should say in the nuclear C-star algebras in this class, satisfy the König theorem for tensor products. And this is used ubiquitously in classification. So theorem, it's an earlier theorem due to Schocket. If A is, if A is in this and nuke, then for any B, there's short exact sequence. All right, so this is going to relate the K theory of tensor product to the tensor product of the K theory. And this time, it is going to be that K star of A tensor B is K star A tensor K star B modulo torsion. So we have 0 goes to A star A tensor K star B goes to K star A tensor B goes to torsion of so this would be a degree 1 mark. So 12 A star A star plus 1 B. All right, so in particular, if K star A or K star B is torsion free, then this is an isomorphism. Isomorphism. If K star A or K star B torsion free. So, I mean, from this, you can deduce, for example, right, remember this Jiangsu algebra Z has the same K theory as the complex numbers. So from this, you can deduce that, and by the way, the Jiangsu algebra, it is a limit of type 1 C-star algebra, so it does satisfy the UCT. So I can deduce, I can apply this theorem for any C-star algebra B. So for any, let's say for any A, the K theory of A tensor Z, so this Jiangsu algebra, is so let me remind you here that K star Z is the same as K star C. So the K0 group is Z, the K1 group is 0. It's torsion free in particular. So I do have this isomorphism. So this is isomorphic to K star A tensor K star Z. But you know, in 0 degree, this is K0A tensor the integers, so just K0A plus K1A tensor 0, so that doesn't appear. So K0 is just the same, and similarly K1 is just the same. So this is K star A. Right. So tensoring with the Jiangsu algebra does not do anything to K theory. And then it also doesn't do anything to traces, which I will talk about very soon. That's why being Z stable is kind of a necessary condition for being in this classifiable category of C-star algebras, because the Elliott invariant cannot distinguish between A and A tensor Z. Right. So this is one very common use of this UCT class in the classification program. We know how to compute the K theory of tensor products. I would say that these days, the real use of the UCT is made very apparent in this work of Chris Schaffhauser and his co-authors. Maybe I'll just sort of say this in words. So Schaffhauser and his co-authors, they show how the UCT is used to solve certain lifting problems. Right. In a way that I really don't have time to get into, but I think if you look at, so Chris Schaffhauser, he has this paper where he gives a new proof, a new short proof of this Diquitius White-Vinter theorem, the theorem that faithful amenable traces are quasi-diagonal. So it's a very important theorem in the finishing up of the classification program. And his approach to this is to set it up as a lifting problem and then use the UCT very directly to solve this lifting problem. So the UCT is often, when someone is giving a talk on classification, it's just stated at the beginning as some sort of magical thing that we'll never talk about, and it's not really clear what it's doing there. I think it really becomes quite clear when you look at this this work of Chris Schaffhauser, and also this with his co-authors Jose Carrion, Jamie Gabe, Aaron Diquitius, and Stuart White. This paper that they put in a couple of weeks ago, where they are giving a new proof, or a sort of self-contained readable proof of the classification of C-star algebras. The theorem that I mentioned on Monday, they take this idea that Schaffhauser has and they really run with it. So this is the framework of what they're doing. Okay, so
Sorry,
yes.
I don't know some other algebra than Jiangsu satisfying this property.
O infinity. The Kunz algebra O infinity. It has this. It also has this same K theory as the complex.
And K theories, I don't remember. It's also
It's the same.
torsion free.
It's this. It's the K theory of the complex numbers. It's the same K theory. So there's the thing that distinguishes O infinity from the Jiangsu algebra is that the Jiangsu algebra has a trace. It is the stably finite version of O infinity.
Does stability with respect to Z imply this stability with respect to these others?
Other way around. So if O infinity, Z stability is the weakest notion of stability with respect to any of these kinds of algebras. O infinity stability implies Z stability. They are both examples of what are called strongly self-absorbing C-star algebras. So in particular, so algebras in this category E are Z stable. The category E, remember I said, was things that are infinite dimensional, simple, separable, unital nuclear, but finite nuclear dimension, actually. That's satisfied the UCT. Okay, so Z itself is in this category. So Z tensor Z is isomorphic to Z. That's the self-absorbing part. Similarly, O infinity tensor O infinity is isomorphic to O infinity. Other examples would be O2, UHF algebras of what are called infinite type. And you can also take tensor products of O infinity with UHF algebras. So these are all isomorphic to their tensor products with themselves in certain strong ways. These are of particular importance in classification. So the classification of purely infinite C-star algebras is essentially classification up to O infinity stability, and it turns out that they are in fact all O infinity stable. Say, all right.
And tensoring with respect to this self-absorbing.
Yeah.
algebras.
Yes.
It's like a localization of the category.
Exactly, absolutely, absolutely. In fact, I think Wilhelm has a paper where he more or less uses this terminology, localizing the other conjecture. I think even they call it, yes. So, all right. So let's pause and reflect where we are at the moment. Now we've discussed all of the hypotheses in the classification theorem, right? We discussed finite infinite dimension. Now the use of T. I kind of described what you need to check that the algebra is simple. And as for the components of the Elliott invariant, so far we've seen K0, we've seen K1. We have not seen the rest. So I want to get to the rest today. So I want to, by the end of today, at least describe in full all the components of the Elliott invariant.
In this exact sequence, your notation of a tensor product, this is a graded tensor product, right?
Yes. Yes, sorry.
The way you write it is confusing.
Yes, I apologize for this. So what I mean by this is that in degree 0, it's K0 tensor K0, direct sum K1 tensor K1. And in degree 1, it's K0 tensor K1, direct sum K1 tensor K0. Yeah, but it's a good point.
And another sort of self-absorbing sister algebra I didn't mention is, I guess, compact operators.
That's true. That is true, but okay, there was over the years, there was some efforts to compact operators is non-unital.
Yes.
There's some efforts to understand what it should mean for a non-unital C-star algebra to be strongly self-absorbing. All the ones I mentioned to you are unital. Right? It's not so clear what it would mean for non-unital C-star algebra to have this property. But one thing is clear that complex operators should not. These should not be strongly self-absorbing, whatever the right non-unital. But there are some other C-star algebras which are known candidates for what should be, and these are in fact stably projectionless C-star algebras. Let's not
Different stories.
different story. Let's not get into it. All right. So my goal now is to describe, as I said, the rest of the Elliott invariant for you. Maybe I just remind you what it was. LA. It was K0A, K0A plus, which I have not told you what it is. I'll tell you what it is now. The class of the unit in K0A. Okay, we know what K0 is. It's just the class of this projection. That's what this is. Also K1 of A, which we also saw. What I'll tell you about soon is the traces. And then we have this pairing map between K-theory and traces, which is just evaluation. All right, so this is the image of V of A in K0 of A. Right, remember K0 was defined as the Grothendieck group associated to this semigroup. So this, we have a map then from V of A to K0 of A, and this map is in fact injective precisely when V of A has cancellation. Right. So this is so this structure K0 plus 1 of A. This is well, okay. It is a what's the terminology? I want to say it's an ordered abelian group, but it's not quite an ordered abelian group. It's in the stably finite case it is. Maybe I'll just say this: an ordered abelian group. If A is stably finite. Ordered abelian group with distinguished order unit. So with distinguished order unit. What do I mean? Ordered group means you have this group G and you have this distinguished semigroup G plus, and you want, first of all, G plus intersect minus G plus should be 0, and also G should be of the form G plus minus G plus. So in other words, every element in G should be able to be expressed uniquely as a difference of elements in G plus. That is the case for the stably finite branch of the classifiable tree. For the purely infinite algebras, this order structure is actually fairly degenerate. In fact, K0A plus is just all of K0 in the purely infinite case. So, so if A is purely infinite, this is a fact I'm telling you, this needs proof, but it's true. So A purely infinite implies that K0A plus is K0A. And in fact, remember, so what characterized pure infiniteness was the non-existence of traces. If you have a trace, you're stably finite. If you have no traces, you're purely infinite. So for purely infinite C-star algebras, this whole big long thing becomes much simpler. So this doesn't appear, it's just the whole of K0. This is the empty set, so this doesn't appear. So it's really just K0, K1 class of the unit. So this, in this case, L is just K0A, the class of the unit.
So all infinity is purely, right?
Yeah. So purely examples of purely infinite C-star algebras are these Kunz algebras for n. So e.g.
Red one.
for n, the C-star algebra of graph E, if E is a, let's say, finite, strongly connected graph. Yeah, I mean, I don't actually, you probably don't need finite. Finite will give you some unital, but let's just say if E is a strongly connected graph.
With finitely many vertices,
Yeah. Okay.
if you want unital.
If I want unital, but
Okay. And strongly connected means that there are directed paths both ways between any.
yeah. So for any vertex I and vertex J, there's a path I to J. All right.
You don't have any simplicity there in
Okay. Let's say yes. I mean, I only defined for you pure infiniteness in the simple case. So let's say yes. But maybe that's not even needed actually. But let's for the moment just say yes. All right. Let me mention now Elliott's theorem, the classification of AF algebras, which is another case where the invariant becomes simpler. So for AF algebras, remember, AF means a direct limit to finite dimensional C-star algebras. Every finite dimensional C-star algebra has trivial K1 group. So AF algebras have trivial K1 group. So this disappears. In fact, this also does not appear in Elliott's theorem. So let me tell you Elliott's theorem. So from 1976, I think. So if A and B are AF, then A is isomorphic to B if and only if this structure K0A, K0A plus 1A is isomorphic to same thing with B. All right, what I mean is there should be a group isomorphism from K0A to K0B that preserves the positive cone and sends the unit to the unit. If A and B are unital AF, let's say. So note that this does not require simplicity. This holds for non-simple AF algebras as well. Simplicity can be detected from the structure of the invariant. So if this is a simple ordered group, then the algebra will be simple, if and only if.
And now I might understand that when you have this isomorphism from K0A to K0B with these nice properties, and then by the theorem, you know that A and B are isomorphic, does it mean that there exists an isomorphism which induces?
Yes, exactly. Yes, it is a functorial classification.
Thank you so much.
And in fact, you don't even need unital for this, except then you don't talk about the class of the unit. You speak about what's called the dimension range of the scale. You look at the distinguished collection of projections that are actually in A, as opposed to in matrix algebras over A. So that could be preserved as well. All right, I'm not going to go through the proof of this. The proof is by what's called an intertwining argument. So actually in next week in Ben Level, this Beyond the Horizons thing, I will talk about the classification of UHF algebras. It's a similar intertwining argument. So I don't know, mini advertisement for the small subset of people who will also hear that talk. All right. Let me mention that the reason the traces, so K1 is 0, that's why K1 doesn't appear. But the reason traces don't appear is that, so the theorem, if A is an exact C-star algebra, and it's what's called real rank 0, real rank 0 means that every self-adjoint element can be approximated arbitrarily well by self-adjoint element with finite spectrum. In particular, this finite AF algebras are real rank 0, and a particular necessary condition to being real rank 0 is that linear span of projections is dense. So span Raj equals A. Okay, so this is automatic for AF algebras. But anyway, if this is the case, then the spatial state space of A is in fact isomorphic to the states on K0. What I mean is the linear functionals, the group homomorphisms from K0 to the real line that are positive, they send positive things to positive things, and they send the unit to the unit. So there are two components to this. It's generally true that for any exact C-star algebra, the map from, by the way, so how does a trace give you a state? It's just this, again, it's just the evaluation map. So let's say this map is RA, so RA acting on some projection or different projections, it's so this map RA is always surjective if we have an exact C-star algebra. What's true is that all such states are given by these posi-trace things that I mentioned. Exactness tells you posi-traces are traces. So that's why this is surjective. Real rank 0 tells me that it's injective as well. All right. So that's why the traces, it doesn't appear in this invariant, because for AF algebras, it's already contained in this information. Okay, but in the non-real rank 0 setting, you need to include it potentially. Maybe
I don't understand this notion of state of such a triple.
So it means
what AF?
It means
It would. Yeah.
it means a group homomorphism from K0A to the real line that is positive. So it sends elements in here to the positive real line, and it's unital, sends the class of the unit to 1. This is what a state.
Yeah, but this positivity is on the level of A0A plus. It's not on the level of positive self-adjoint elements.
No. When I say positive, I mean this is the positive component in this ordered group. I mean, it's defined on projections, not on positive elements.
In the case of AF algebra,
Yes.
does the space is the same as the space of state?
No. It's a space of traces.
Oh yeah,
That's what the content of what I'm saying here. Don't think that this is related to the states of the C-star algebra. It's just the same terminology, but I think for a good reason. It has similar properties to states. It's not my terminology. So if you're unhappy with it, I apologize. But let's move on. It's anything else unclear?
You didn't actually define if this K0A plus, but this is the image of VA. You did. Oh, I'm sorry. Okay, so it's the image of VA under.
Yes.
Okay, sorry. Maybe because of this construction noise, I didn't hear.
Fair enough. And anything else? Okay, all right. Maybe another thing I'll mention. Right, so I said it's already contained this information in the AF case, that's why it doesn't appear, but then I said in general you might need it, need to include traces. Why? Here's one kind of striking reason why. So this is due to Elias Farrar, Andrew Toms, and Asger Turnquist. And the theorem is that this class E, the class of infinite dimensional simple separable unital finite infinite dimension UCT C-star algebras, cannot be classified by countable structures. This can be made precise using a notion of Borel reducibility. Let's not get into that. So in particular, ordered K theory, it cannot be enough to classify this this category E. All right, yes, okay. This was known well before this theorem appeared, that you need to potentially include traces. This was already known by work of Goodall and Klaus Thompson from the early 90s, that the traces were needed. But I think this makes the point quite starkly. So we need something to account for the complexity of this category. And the thing that brings the complexity is exactly this structure of traces. So let me finally then.
So, but why is obvious that this K0 group is not countable?
If it is separable.
Very separable.
It is separable, yes. So I think I mentioned last time that if you have a 2-1 factor, 2-1 von Neumann factor, and I believe that the K0 group should just be the real line.
Exactly.
Which is in particular not countable.
Yeah.
Okay, so finally then, let's get to traces. What is a trace? What kind of structure does it have? All right, so let's say that all the time A will be separable and unital. Neither of these is really necessary for what's strictly necessary, but it'll just make some things significantly easier. So a trace from A to the real line is a trace, by which I mean a tracial state. That is a positive linear functional of norm 1 that satisfies the trace identity. The trace, if it is positive, so if it is a positive linear functional, with norm of trace equals to 1. So that's in the non-unital case, this is what you require, but in the unital case, equivalently, this is.
So you allow only real linear functions.
Yes, sorry. No, I didn't read this. No. Sorry. Thank you. Positive linear functional and satisfies the trace identity. So one way you can phrase the trace identity is that the trace of U star is the trace of A for every A and for every unitary. Right. I mean, this is equivalent to, trace XY equals trace YX. Yeah, exactly. Right. Maybe let me straight away state theorem. Just due to Homer. Which is that the maybe I should write so trace tau A is T of A is the collection of traces on A. That's what. So when I write when I've been writing this T of A all the time, this is what I meant. These kinds of functions. And the theorem is that this is what's called the metrizable showcase syntax. And I'll tell you now what that is. Right. Couple things. First of all, if you look at Thomas' paper from the 60s, okay, first of all, it's in German. But more importantly, if you look at Matthias, I might have other points. Maybe not such a big deal to some, but more importantly, you will not see anything about showcase syntheses in this paper. There is another paper also from the 60s by Peterson, where he also proves this result, but again, you will not see anything about showcase simplices. What they prove is that the cone that this compact convex space generates is a vector lattice. This is equivalent to being a showcase simplex. I just wanted to mention that in case you go chasing through the literature and don't see this written anywhere.
Different showcase.
The first one is
When
Yes.
I know, all I know is that it's not pronounced showcase.
Okay.
And by the way, so this metrizable here is why I wanted separate. Right, it's a bit more complicated. It's quite a bit more complicated to describe what a showcase simplex is in a non-separable case. Let's not get into that. All right, so I want to now kind of describe to you what this means. So a showcase simplex is a certain kind of compact convex space, so is a special kind of compact convex subset of a topological vector space, of a Hausdorff topological vector space. Okay, what is the ambient topological vector space in this setting? It's the dual of A. So T of A, the space of tracial states, lives in the dual of A. And the topology is the Weak-Star topology. In other words, the topology of pointwise convergence. So a net of traces converges to some trace, or if it converges pointwise. By the way, okay, this is compact because we know by the Barnack-Kalioglu that the unit ball, this dual, is Weak-Star compact. This is a closed subset of the unit ball. I mean, the conditions defining it are closed conditions. It's convex. If I take a convex combination of traces, I still get a trace. So lambda tau 1 plus 1 minus lambda tau 2 is still a trace if tau 1 and tau 2 are traces. Okay, so to motivate the definition of what a showcase simplex is, let's think about finite dimensions. I think we sort of know what a simplex should be in finite dimensions. And this will inform the definition in the general case. So in finite dimensions, a simplex is the convex hull of a collection of points that are affinely independent. Is the hull of finitely many points finitely many affinely independent points. Right, affinely independent means I have some points. If I shift one to the origin, then the others should be independent. Okay, so for example, just a point, right? If I shift that to the origin, there are no others. So the others is the empty set. They are independent. This is the simplex. So this is the zero-dimensional simplex. The one-dimensional simplex is just the convex hull of 2 points. Three-dimensional simplex is a triangle. You know what? Maybe let's do this. And let's see if I can successfully draw a tetrahedron. Maybe not.
Then you have to leave the surface of the.
Yes, I mean, I really could have done a better job there, but okay, I hope you know what I mean. Right. So these are what we think of as finite dimensional simplices. The points that I've written in red are the extreme points. These points that give us the convex hull. So the red points are so let's say these is a special kind of compact convex subset K. So I'll write it like this, delta EK. So this is the collection of extreme points. Of K. Right. Extreme points means precisely that I cannot write this point, say, as a proper convex combination of two other points. So maybe I write this out. So extreme point, it means following. E extreme means that if E is lambda, let's say X plus 1 minus lambda Y, for some lambda in 0, 1, then X equals Y equals E. So, I mean, for example, for a circle, every point is extreme, but this is not a simplex, because the extreme points are not affinely independent, right? So it disagrees with what our kind of notion of simplex should be. Let me now rephrase this condition of being convex hull of these affinely independent points as in terms of what's called an integral representation theorem. So let's write. So this also appeared at some point on Monday or something. So let's write f k for the set of, so K is this fixed compact convex subset of a topological vector space. Let's write f k for the affine functionals on K. So the continuous affine maps K to the real line, real values. So affine means that f of lambda x plus 1 minus lambda y is lambda f of x plus 1 minus lambda f of y. All right.
Convex.
Yeah, K is this fixed compact convex subset of this ambient vector space. Wait, so what I want to do is let's fix the point x and k, x and k. Let's assume that for the moment K is one of these finite dimensional simplices. Then this X can be uniquely written by independence as a convex combination of these finitely many extreme points. So and X is uniquely of the form X is the sum of I equals 1 to n lambda I EI. So where let's say the extreme points are E1 to En.
Why not from I equals to 0 to n?
Labeling them for what?
Sorry.
I'm labeling them for what? It'll have done from zero. I can never.
-5. Let's start at -5.
No, zero is,
Oh, all right. No,
so then n is the dimension.
sure, I'm happy to.
Otherwise, the dimension is n minus one.
No, I mean, you raise a fair point. I think in practice, I would actually do this. So easier at the end. All right. Now I want to apply an affine function f to it. And what I'm going to get at is I want to show that evaluation on some affine function f can be interpreted as an integral. So let's see why that is. If I take one of these affine functions, then f of x is f of the sum.
By the way, you have a chance of not running out of screens because after 1 hour of your talk, you have 10 of blackboards.
That's good to know.
Still 9 pages.
Yes,
Well, like you just started.
but it's good to know my
At
step.
the right speed.
Right, excellent. All right. So it's this complex combination. Now it's affine, so I can put it into the sum. So this is the sum of lambda I f of ei. But I can interpret this as an integral. So this is the integral over k of f d mu x. So where mu x is this convex combination of point masses at each of the extreme points. So this is the point mass at ei. If I integrate a function with respect to a measure, and the measure is just concentrated at one point, that integral is just evaluation. Okay, so the integral of f with respect to one of these is just f evaluated at this point. Right, so if I take a convex combination, then the integral is just this convex combination. Okay, so this is why this sum is equal to this integral. To another
Important is a probability measure.
Yes, absolutely. So in fact, more is true. So this is a Borel probability measure. And it is supported on the extreme points. I mean, that is what's really crucial. Because, okay, I said, if I take the point measure at the point mass at a point, and integral is just evaluation at a point. So then why don't I just define mu of x to be point mass at x? Right, then integral of f with respect to that point mass will just be f of x. Okay, but that doesn't tell me anything. I want this measure to be supported on the extreme boundary. That's the crucial thing here. So what this shows is that for every x, there is a measure on the extreme boundary such that evaluation of any affine function is just integral with respect to that measure. And in fact, by linear independence, this measure is unique. So in fact, so this mu of mu.
Define independence.
Yes.
By define.
Yes. Okay, by affine independence. So conclusion here. So given x in K, and for the moment, I'm just assuming K, remember, it's just finite dimensional here. There is a unique mu of x supported on the boundary, the extreme boundary. Such that f of x is the integral over k of f d mu x for every affine function. This mu x is what's called a representing measure for x.
Rate is supported. It will be not.
What do you mean erase the support?
Because usually if you say the measure is supported on some set, you are speaking about the subset.
Yes.
When this measure is supported.
Yes.
Of course, this boundary this extreme points. It's a subset of this simplex, but its measure is not defined on this simplex. It's defined only on this set of extreme points.
Sure. So I could, instead of K, I could write
Yeah.
the extreme boundary here.
So it's better to erase the supported because it's a measure on the space of extreme points. is a
But I
measure.
can also interpret it as a measure defined on the whole space.
Yes, but not.
What do you mean by? all
Just
space?
the measure of any set supported on
You
the
are subsetting
subset.
by zero.
Yes, yes,
Defined space.
Yes.
Setting the simplex.
yes. So a measure on a space to be supported on a subset means that the measure of any subset is the measure of the intersection with the set on which it is supported. I see nothing wrong with what I've written.
Yeah, I concur.
No,
No,
because sometimes.
no, let me disagree with you strongly because of this point that I made, because every affine function can be, every x can be represented by a measure at x. So there is some measure on the whole space, namely just supported at a point x, not on the boundary where this is true. So it is crucial to make the distinction that there is, in fact, another measure that lives on the boundary. Okay, we'll just argue semantics now if we continue this discussion.
Okay.
Okay, so and in fact, this is the definition of what a showcase simplex is. So this definition, I'm saying for you, with our agreed upon notion of what a simplex should be in finite dimensions, this is true. All right, so if we take some points that are affinely independent, then we get this unique represented measure. In general, this is what we mean by a showcase simplex. So definition. A showcase simplex in infinite dimensions potentially. Okay, metrizable showcase simplex. Is a compact convex set K. Set K, such that every point in K is uniquely represented by a measure, by a probability measure. On the boundary. Right. So examples would be any finite dimensional simplex according to our understanding of what a finite dimensional simplex is.
It is always metrizable.
Okay, let me address this metrizable issue. Assuming that K is metrizable, you can show quite easily that this extreme boundary is a G delta set. In particular, it's Borel. So it makes sense to speak about a Borel probability measure supported on such a set. In the non-metrizable setting, it may not be a Borel set. And then you have to be a bit more careful about what you mean by something like this. It is possible to say something in the non-metrizable setting. I think maybe, I can't remember how it was, maybe Choquet addressed the metrizable setting and then Bishop and Deleuve did the non-metrizable, something like this. I don't know, but I don't want to get into this, so metrizable all the time. A couple other comments. The Klein-Millman theorem, you may recall, says that a compact convex set is the closure of its extreme boundary. So every point in K can be written as a limit of convex combinations of extreme points. You can interpret that as something similar to this, except you get a measure supported not on the boundary, but the closure of the boundary. The second statement is that
Closure in K.
closure in K, yes. Second statement is that it's a theorem of Choquet that for any compact convex set, you always get at least one representing measure that lives actually on the boundary, not on the closure. So the requirement that this is unique is what makes a Choquet simplex special, as opposed to a general compact convex set. All right, let me give you some examples of Choquet simplices. All right, so first of all, as I said, the finite dimensional simplices. Wait, I already told you the theorem by Thoma, where it was that the tracial state space of any separable unital C-star algebra is a showcase simplex. So take any T of A for any A that we've been talking about, that would be an example of a showcase simplex. Okay, so the finite dimensional ones, these are examples. Maybe somewhat more interesting example is if we take the space of Borel probability measures on a fixed compact house of space X. On X, so that is compact house. Actually, this is itself it falls under Thomas theorem. So this is by the Rees representation theorem, or one of the Rees theorems. This is the space of states on C of X, or equivalently the space of tracial states. Tracial in the commutative setting is not any more restriction than just being a state. So this is traces on C of X. Right, so and any state on C of X is just given by integral with respect to one of these measures. In fact, this is a very special kind of showcase simplex because the extreme points, so the extreme points of this are just the point masses. So let's say this is okay. So in this case, the extreme points is X. So you send point X to the point mass at X. And that this is for, functional analysis, blah, blah, blah. I mean, this is an isomorphism, a homeomorphism, sorry. Okay, so this is what is, so in particular, the extreme boundary is compact. This is what's called a Bauer simplex. So this is compact. So K is a Bauer simplex. Bauer simplex by definition is showcase simplex where this extreme boundary is compact. So both of these, I mean, the finite dimensional case, yes, in fact, the finite dimensional case is also a special case of this. These are Bauer simplices. In fact, every Bauer simplex arises in this way. Any showcase simplex where the boundary is compact is measures on some compact space X. Okay, let me give you a sort of on the flip side of this kind of tame example, you have what's called the Poisson simplex. And the Poisson simplex, the defining property of it is that the extreme points are in fact dense in K. So, all right, okay. It's not zero-dimensional simplex. So it's infinite dimensional simplex where the extreme points are dense. So it's something very much more complicated than this situation here. It is, if you know this terminology, it's what's called the Frese limit of the category of finite dimensional simplices. Okay, but in fact, any metrizable showcase simplex arises as the tracial state space of a classifiable C-star algebra. So you give me any showcase simplex you want, I can give you a classifiable C-star algebra with that as its trace space. In fact, you can do that using, for example, AF algebras or AI algebras. And that is a consequence of, maybe I mentioned this. In fact, there's a theorem due to Lazar and Lindenstrauss. Which is that any showcase simplex, any metrizable showcase simplex is a projective limit of finite dimensional ones. Any metrizable showcase simplex is a projective limit of finite dimensions. I mean, you could almost take this as the definition of the showcase simplex. In many contexts, this will do. In the next half of my talks, I will be in fact using both pictures of what a showcase simplex is. So I'll be using this picture that you can build it via limited finite dimensional. Once I told you one of the applications I wanted to get to was some kind of probabilistic constructions, and I'm just going to tell you about essentially a probabilistic version of this theorem. So I will show how to make this limit random. But also in one of the applications, I'll be talking about some sort of dynamics on the trace space, and for that I want to use really the representing measure picture. We'll come back to this.
What's known about magnets in this system?
You can describe it very, very concretely. So they look like this. Yes, yes.
Things are fine.
Yes, continuous affine maps. Yes, in fact, you can say much more than this. So the maps look like this. So it's a limit of, in fact, let's say it's infinite dimensional. All right, so let me describe for you this map here. What it does is we think of this as being the base of this. So the map fixes the base and it collapses this point somewhere in the middle. Similarly, here to here. Okay, but here there's no choice, but here, let me fail to draw a tetrahedron for you.
And it is independent of the choice of this point. It could be even some boundary point of this small.
It could be, but yes,
Simplex.
yeah, it could be. So here again, you fix the base and then you map this somewhere inside.
So you could contract find one face, for instance.
Contract
Three
one
faces.
face? What do you mean?
No.
Yeah.
So we are contracting a face.
Yes.
Yes.
Yes. Yeah, that's all it is. And but depending upon the points you collapse to, you get a different simplex, of course. By the way, this is how the random construction will work. I'll say, okay, let's just collapse to a random point.
In terms of why you say independence, same simplex. With this point on this simplex, they are no longer independent, so they are not extremal points.
Okay, and maybe I'm not understanding the comment or the question you were making. So what
Collapsing, what do you mean by collapsing?
So I mean, what I mean is, to tell you what this map is, I need to tell you what it does to the extreme point.
Assignments.
It sends this extreme point to this one to this one, and this one is somewhere in between. And then the points inside I determine by convex combinations.
For instance, the that point of this segment.
Yeah, absolutely. That's a perfectly valid choice. Yeah, I could do this.
A canonical choice because there's an order on.
Sure. In fact, if I did that, if I just did that all the time, I just collapse this to, let's say, to this way it makes all the time. What would I get? I would get, in fact, Bauer simplex, and I think the boundary would be sort of the minimal infinite compact space, so the space of a convergent sequence. I think that's what you look at.
So can you say again what this Bauer simplex is?
It's a showcase simplex where the boundary is compact.
Okay.
But this is quite special, as the Poulsen simplex kind of demonstrates. All right. Okay. All right. So now we know what a trace is, and we know what the structure of this is. And as I say, so the metrizable showcase simplices, they can be quite complicated, like this Poulsen simplex. So that's really where the complexity of this classifying invariant is coming from, right? As I said, it can't be classified by countable structures. The complicated thing is really happening here. All right. So I've now, at the moment, described for you all the adjectives in the statement of the classification theorem. I'm going to describe for you the components of the Elliott invariant. There is, I have enough time, more than enough time to tell you what
And enough blackboards.
I should have enough blackboards. Let me say that so I mentioned that the classification of AF algebras that George did back in the 70s was via this, what's called an intertwining argument. I mean, just to give you a rough idea, okay, so this is an AF algebra. It's a limit to finite dimensional, guys. I apply the K0 counter and I again get a limit. So this is what's happening for A, this is what's happening for B. So I have a similar thing happening here. So think of these.
It's a system, it's not a graph.
It's a system. It's an inductive system, is what I'm describing. An inductive system of K0 groups, let's say. Then what I do is I have I'm assuming that I have some isomorphism in the limit. Right, well then what I do is I kind of do a back and forth argument. So this maps into there, but this is a finitely generated object. So I find some object into which it maps such that this commutes. Then I go back up. Then I have this map going here. So I map into some finite dimensional stage. And this way I construct a commutative diagram at the level of K0. And then I lift that diagram. I need to show that if I give you a K0 map between finite dimensional C-star algebras, I can lift it to a star homomorphism. Right, and then so I lift this K0 commutative diagram to an actual commutative diagram of C-star algebras. And then that'll give me the C-star algebra homomorphism map inducing the isomorphism. That's how the argument goes. What I want to say is that the classification of, so that's how it goes for AF algebras. But if you want to do AI algebras, and also limits of these dimension drop algebras, of which the Jiangsu algebra is an example. They also depend on some intertwining argument. But it's more complicated now. It's more complicated because we don't just have K0. We have potentially also K1 and potentially also traces. And then when we do an intertwining of K0 of finite dimensional things, we really can't get an on-the-nose commutative diagram. It really actually commutative. But when we have to throw traces into the mix, we get only approximately commutative. All right, this is not such a big deal, but it is something you have to account for. So this is also by intertwining using also K1 and traces. And indeed, you need to do things compatibly. So you need to take a pairing between K0 and K traces into account for this pairing up. K0. Okay, but it's still the essence of the argument is it's the same thing. It's intertwining argument. This is a kind of segue into what the next thing I want to tell you about today. So as I said, the classification of AF algebras, it works even if you don't assume simplicity. That's also true in the AI case. So the class of approximate interval algebras, AI, let me just remind you, means that the building blocks are continuous functions from 0, 1 into something finite dimensional. So it's limits of things like this. In fact, so these algebras are also completely classifiable, not assuming simplicity necessarily. But to get the non-simple objects, such limits, the Elliott invariant is not enough. So it's not classifiable by K0 and then traces. You need to use what's called the Kunst semigroup, which is what I'll tell you about now. So the Kunst semigroup, which I will define in a moment, it's defined very much like the Mary von Neumann semigroup, except instead of projections, you're looking at all positive elements. And it's big enough to, in fact, contain the ideal structure of any C-star algebra. So the Kunst semigroup, that's why it is often a useful tool in non-simple classification, because the ideal lattice of the algebra is contained in the Kunst semigroup. Okay, so let me tell you briefly, because I do want to use the Kunst semigroup, in fact, when we get to the applications. So let me tell you what the Kunst semigroup is and what it looks like in some examples.
So can you briefly remind me why you call these dimension drop algebras?
It's a good question, and I never really addressed this. I mean, the name is descriptive. They look like this.
Like, so.
Yeah.
Also here you use the same argument for approximate dimension drop, you said for AI.
Yep. And also for this, In fact, so AI, it's not so bad because there's no K1, yeah. So it's just K0 and traces you need to worry about. It's really not so bad. And you also need to include K1. And if you look at Jiang and Su's paper, that's where these algebras are classified. It's heavily using KK theory, in fact, to kind of get K0 and K1 information all around. So it's really, it requires quite a bit of structure, actually. But still, the starting point is still this intertwining.
Sorry, so all these arguments are about isomorphism between our.
Yes, there are also homomorphism theorems, which work in varying degrees of generality. So in the AF case, yes, homomorphisms will also work.
You can rephrase this.
Yes, as a homomorphism.
Interior invariant to be a covariant functor, and then.
Yeah, but this is.
Can you speak about?
Yes, but. Okay, but. If you want to speak about homomorphisms, it was isomorphisms. In general, the element invariant will not be enough. You need to refine it. You need to. I'm going to talk about this in a couple weeks. You need to include also algebraic K1, and really that's the missing ingredient. You potentially need to include algebraic K1 as well.
Algebraic K1.
Hausdorffite unitary algebraic K1 actually. Really, I mean, so this is a notion introduced by Klaus Thomson, that's well in the setting of sister algebras. But it's really a crucial part of a lot of the classification results, and certainly in this paper by Jose Carrion and his authors. I mean, it's really front and center there. It's really an important part of the invariant. And even in the case of maps into the Jiangsu algebra, which has no K1, you still need to consider this algebraic K1 potentially. The thing is, if you're talking just about isomorphisms, then an isomorphism of the L invariant will extend to an isomorphism of the algebraic K1, but just endomorphisms, maybe not. Yeah, potentially more complicated.
Maybe it's really K1 K1 such thing for algebraic.
Sorry, say.
K1 goes up. Yeah. As a marking for topological algebraic, only K0 is the problem.
K1 is different.
The other one, K0 is okay.
Algebra is not bigger.
But from algebraic K1 to.
Yes, exactly. Indeed. But I'll tell you about algebraic K1 next half of the course. Okay. All right. Sorry, I was addressing the question, which was why is it called dimension drop algebras? Because the dimension of the irreducible representations drops.
So representation, because I wanted to see which dimension drops. Okay.
The bigger one.
The smaller one.
All right. So in the interior of the interval, irreducible representation is point evaluation has dimension PQ. At 0, you have to look inside this block. So the dimension is P, and at the other, the dimension is Q. So you have, the dimension drops.
I would just call them joint algebras, joint sister algebras.
I see. Okay, so let me now tell you about the Gunch semigroup. Okay, so this will be defined, as I said, similar to the Merritt-Van semigroup. And the starting point for that was equivalences of projections. So let me tell you about equivalence of positive elements. So for A and B, positive elements in a C-star algebra A, say that A is Kuntz's subequivalent. And write like this. Do that a bit better. Subequivalent to B. If there is some sequence xn such that A is the limit of X and B, X and stuff. I'll give you some examples of when this holds up shortly. And the Kunz equivalence is just the symmetrized notion of this. So if A is smaller than B and B is smaller than A, we say A is equivalent to B. Say A is Kunz equivalent. B, A, then B, if A is smaller than B and B is smaller than A.
You don't assume xn to be something like consonant symmetry.
No, just some elements. I'm not assuming anything about even the norm or anything like this, some sequence development. All right, and then the Kunz semigroup is I look at positive elements in the stabilization of A modulo this equivalence relation. So the Kunz semigroup CUA is defined to be A tensor K positive elements modulo this. Right, and here it actually makes a big difference whether I take A tensor K or M infinity of A. So I do not get the same object. In fact, Kunz in his original study of this semigroup, he took not the compact operators, but he took essentially M infinity of A, positive elements and M infinity of A. The difference, one of the reasons why this one is used more prevalently these days is that this is continuous with respect to inductive limits, whereas the other one is not necessarily. It may be, for example, a stable rank one set, but in general, no. And sort of crucial, what's crucial to that is that, okay, so what this is a positively ordered monoid, in fact. Maybe I can write this down. So it's a positively ordered monoid. I mean, okay, maybe it's positively ordered monoid.
Is there a natural map between them? If one uses
yes,
tensor with K, not
yes. I think from the M infinity one, there is a map into the CUB.
What's the K theory to?
Sorry, for K theory?
Yes, from K theory to Kunz.
Yes. I'll mention this just now. There is a map from V of A, the Marino-Neumann semigroup, into CUB. There is a map. I'll get to this shortly.
Yes, indeed, there is. Yes, it's the obvious.
We'll talk about this shortly. So this C is a stable additive continuous functor. Into what's called the Kunz category. All right, I'm not going to define for you what the Kunz category is. It's not just the category of positively ordered monoids. There are several other axioms that it should satisfy. In particular, one of them is that it should have every element should be the supremum of an increasing sequence of elements. And indeed that suprema of an increasing sequence exists in this guy.
So is this factor essentially subjective?
Remind me what this means.
Do these axioms for Kunz category determine the image of this Kunz environment?
It's an excellent question, and I don't think that's known at the moment. I did all the time. So the axioms are called like O1, O2, O3. I think there might be up to 09 or something by now. They keep finding new axioms that seem to be necessary for C-star. Yes. But I don't think it's known whether it is.
But there's no theorem about the realization of this.
Not yet. I don't know what the state of it is. But yeah, no, it's an excellent question. Okay, so but as I said, it's continuity with respect to inductive limits that holds for this, but not the M infinity version. And this property of being having supreme of increasing sequences is kind of crucial to this. Okay. Let me give you some examples of Kunz equivalences and Kunz semigroups, just so this you have an idea. All right. So first of all, Kunz equivalence, Kunz subequivalence of projections is the same as just normal subequivalence of projections. So P is Kunz smaller than Q if and only if yes, right, exactly. It's P less than or equal to Q. If P and Q are projections.
I'm sure you mentioned it, but you use the suggestive notation, which looks like an order. So you have transitivity, right? No problem.
Yes,
No problem. Yeah.
no problem.
The very definition.
Yeah, okay, so there is an alpha map. So the map from the Murray-von Neumann semigroup to CU.
That's nice.
So just the class projection, the Murray-von Neumann class to the Kunz class, this map always exists. It is injective if A is stably finite. So this is injective if A is stably finite.
In the semigroup homomorphism, right?
Yes. Okay, this is an example you should bear in mind. In C of X, for continuous functions, FG in C of X, what does it mean for F to be Kunz smaller than G? It means that the open support of F is contained in the open support of G. So Kunz equivalence just means that the supports are equal, the open supports are equal. So for this, F is Kunz smaller than G, if and only if, let me write it like this. So O for open support, F is contained in open support of G. So they're equivalent. Yeah, I mean, this.
So if F and G are positive.
Yes, thank you. Yes. Yeah, it's only defined for positive. Yes.
Why do you restrict the definition to only the positive ones? Without the restriction, you would just get a ordered group? Or is there something that breaks down in the definition?
This is a good question.
Yeah, you're right. It could be better to define the positive cone inside of something.
I mean, it's actually a reasonable question, which I occasionally pondered. Yeah, you could, let's say, even if you wanted to just consider real value things, you could just look at self-adjoint elements, say.
Maybe that would make more sense.
Yeah. Yeah, at the moment, it's not obvious to me why that would be an unreasonable thing to do. Yeah. It's a reasonable comment. I mean, it could be that for reasons that are just not at the moment apparent to me, that working with positive elements makes certain arguments or certain claims simpler or even true. I don't know, but it's a good point. I can ponder about this. Okay. So this is what Kunz subequivalence or equivalence means in the creative case. I'll tell you shortly some examples of what the Kunz semigroup is for certain commutative C-star algebras. In general, it can be a bit complicated. But first, let me tell you what the Kunz semigroup of the complex numbers is. So, I mean, and this is the same. So CU, I said it's stable, meaning under tensor with the complex. So this is the same as MN. It's the same as, so just like for K theory, same as compact operators. And it is, okay, and guesses for what this is going to be. So what would it mean for two positive elements to be Kunz equivalent in this sense? Okay, maybe let me go back to the definition of what it is. This is perhaps a little bit opaque, this notion of self-equivalence, but if you unpack this for matrices, what you will learn is that A is smaller than B precisely when the rank is smaller. And equivalence is just equality of ranks. So the
Natural numbers.
it's in natural numbers, including 0, but also infinity. Okay, because I'm looking at positive elements in the stabilization. So I need to throw in also infinity. So this is n union infinity. So 0 is a natural number.
You topologize it as semi-group somehow.
Yes, yes, it has the I think that the
1-point compactification.
oh, you mean in general? See,
Yeah.
yes, there is. I mean, whenever you have a sort of ordered semigroup, I guess there's something like the Scott topology or something you could
Related to this order.
related to this order. Yes. Yeah.
So then I think there must be something weird going on in the definition if you extend up to the.
In the definition, we are using the limit. Which says,
The norm limit.
no,
Norm limit.
topology.
The,
So why you are saying about this?
I mean, that's the limit.
Order topology.
That's the limit in the C-star order. So this is a semigroup. This is a positive ordered semigroup, which I could think of putting a topology on this.
So this topology is not induced by this topology of this no topology of the algebra.
How would you? So you're saying the class of A should. No, I don't think this will give you something meaningful, to be honest. I don't think this would necessarily give you something meaningful. But as I said, really, it's the order structure that's of importance here. Okay, let me tell you that now CU of continuous functions on the closed interval. This is isomorphic to lower semi-continuous functions from. Let me denote this by n extended natural number. Right, so I mean, this is by diagonalizing. You take a positive element and you diagonalize. The rank function will only be the function that sends a positive continuous function over the interval to its pointwise rank will be lower semi-continuous. That's why you're getting this LSC appearing. So over this one-dimensional space, you can do, as I say, diagonalizing, and then via mapping to the pointwise rank, you can show that this is an isomorphism. For higher dimensional spaces, it's not necessarily true that you can do this diagonalizing. So that it becomes much more complicated. So C of X is more complicated. In higher dimensions. This is one of, okay, I'm sorry, I told you, okay, CU, it is useful for classifying even non-simple things, and it includes the ideal lattice. It seems great. So why don't we just use CU instead of the LH invariant? It has a disadvantage of being significantly less computable than K theory. It's often quite tricky to nail down exactly what CU is in a meaningful way, but sometimes you can say quite a bit more. So building on this example, CU behaves well with respect to pullbacks, again, in this kind of low dimensional setting. So if A is what's called a one-dimensional non-commutative CW complex, so these are not the CW non-commutative CW complexes that Elmar was talking about a couple of weeks ago. This is the notion of Eilers, Lauren, and Peterson. Non-commutative CW complex. So it means it's a pullback of this form. So A into some finite dimensional C-star algebra E, and sitting over, here's the one-dimensional part. So it the other projection map is into continuous functions from the interval into some other finite dimensional species of algebra F. And then I have some gluing map. So this goes to F, direct sum F. So this, let me say this is some phi, which is phi 0, phi 1. So I have some gluing happening at 0 and at 1. And this is the evaluation map. F0.
Wait, so A is a C-star algebra, right?
Yes.
Well, yeah, and that. Oh,
Finite dimensional C-star
finite.
algebra. So E is, let's say, direct sum of M K I equals 1 to N, and F is direct sum I equals 1 to M L I. All right, so that's what a one-dimensional CW complex is in the sense of Euler-Florin Peterson. An example of this is the parametric graph algebras. You should think of this as algebra of continuous functions from the interval into some finite dimensional algebra with some boundary conditions. So that's what this map here, this map phi is giving you some boundary conditions. And in particular, the one-dimensional, the dimension graph algebra has these boundary conditions. So consider it a little mini exercise to try to write dimension graph algebra in this way. So e.g. dimension graph algebra.
Right, bottom corner, this is E plus F, not FF.
F plus F.
F plus F.
Yeah, I have two maps from E to F. One at 0 and one at 1. So in the case of the dimension graph algebra, this E will be MP plus MQ. This F will be MPQ. So the map at 0 is the map that sends the P component Q times into F. So Q times the diagonal and sends the Q component to 0. And then at 1, it's the other way around.
So really boundary conditions, but at endpoints. Okay. Both.
Yeah.
Okay. Mhm.
All right. And the theorem, which is a theorem of Antoine Pereira and Santiago, is that in this situation, the CU of this diagram is the diagram of the CUs. So in this situation, we have.
Could you come back?
Yep.
If you have this semigroup, the upper example.
Yeah.
N plus infinity. So infinity with respect to this semigroup structure is absorbing an element.
Yes.
An absorbing element.
Yes.
So this will spoil any Grothendieck construction in a sense.
Okay.
So it does make sense to apply the Grothendieck and compare it with K0
Yeah.
of the algebra itself.
Okay. Okay. Yeah, that's a good point.
So it is a very, very interesting point that in this construction, in opposite to the situation of this semigroup of projections, yes, we obtain this absorbing element.
Yeah. And this is related to the fact that we want to have in this structure suprema of increasing sequences.
Mhm.
So we really do want this infinity to be there. Yeah.
So I know you are not responsible for this terminology, but can you give me a hint? I know that the CW complexes are given in terms of pullbacks, but why is it a non-commutative CW complex? So
Because it's a gluing of zero-dimensional things over a one-dimensional thing. And then you can define a two-dimensional complex simpler. You're gluing a one-dimensional thing over a two-dimensional thing.
Yeah, I mean,
but they should have some cells and
but there are functions from one D that you have
this
cells.
is one.
Idea is that the smallest pieces are just matrices, are just some kind of, and then from that you glue some cells and get some higher and higher dimensions.
Yeah, it really is defined like this kind of inductive construction, just like CW complex. It's gluing. Yeah. All right, so maybe I'll just say that. So theorem.
Since it has nothing to do with topological CW complex.
yeah, exactly. That's my because it takes a 1-by-1 matrix to take this number. The commutative is nothing to do with CW.
but you are gluing something one-dimensional with something zero-dimensional.
And that's it.
That's it. So it's one dimension.
Wait, so it's the appropriate callback. I mean, all right, so CU of A, it's additive, so CU of this finite dimensional one will just be a bunch of copies of CU of the matrices, which is N, so this will be N to the N. This will be this lowest semi-continuous functions. So this is CU of the finite dimensional one, so this is N to the M, I guess, and this would be N M N to the 2M, let's say. Okay, so CU of A is going to be lower semi-continuous functions from 0 into this extended power of natural numbers with some boundary conditions that correspond to the boundary conditions of the CW complex. Okay, so at least in this setting, you can reasonably have an idea of what the Kuhn semigroup looks like. All right, so what I finally today, in the last 10 minutes, so 9 minutes, I want to describe to you how the Kuhn semigroup relates to the Alef invariant. First of all, every trace.
Sorry, could you explain why it's for matrices is the power of n?
Because I had a direct sum of matrices.
Yes, I see. Yeah, okay.
Okay, so every trace gives a functional. On CU of A. Okay, so functional, I mean, it's a functional means it's lambda from CU of A to 0 infinity is a monoid map that preserves these suprema. Monoid map preserving suprema. And I really do want it to be in the positive 0 infinity because this is a positively ordered monoid. Everything in here is positive. There is no, I don't want to allow negative values. So via the Kunz class of a positive element, I send it to, all right.
Sorry, if the order topology then preserving suprema means monotone simply.
Is that enough? Maybe this is enough. Or would that just give me one inequality for the suprema? Yeah, I'm not sure. Okay, yeah. No. All right, so I mean, I cannot just define it to be trace of A, like with the projections case, because that will not be well defined essentially, because different representatives could have different traces. But what is well defined is this what's called the dimension function. So detour of A. So I define this to be the supremum or the limit as n in n of the trace of the nth root of A. So this is well defined. So any two representatives evaluate to the same thing there. This is, as I said, called a dimension function. Dually, A gives, in fact, a lower semi-continuous map on traces.
So your statement is that this CU of A is a pullback of the semigroup.
Yes, in this particular case.
Yeah, in this particular case.
I don't think it's generally true that a CU of a pullback is a pullback of CUs, but in this case, yes. Right. So
And by one dimensional, this non-complete CW complex, you mean
interval.
you just have interval.
I'm gluing matrix.
That's what you had before, is it?
Yes, I had before. Okay, so dually, I get just the dual notion of this. So I send a trace to detour of A. So trace gets sent to detour of A. Okay. Yeah, and the final thing I wanted. So by the way, so I guess this is only lower semi-continuous, not continuous. In the case of in the case of projections, what is the nth root of a projection? it's just the projection itself. Square root of P is P. So this, for projections, this is just the trace of P. All right, and that is in fact a continuous map on K theory. So for projections, this evaluation map gave me actually something continuous, but in this more general setting, I get something only lower semi-continuous. So the final thing I want to tell you is that for classifiable C-star algebras, in fact, every lower semi-continuous function on traces arises this way. And in fact, this gives us a complete description of the Kuhn semigroup of classifiable C-star algebras. So here's the theorem. Due to Brown, Herrera, Hans. All right, the reason I put her in parentheses is the Brown-Perrin and associative. Sure, Brown-Perrin and Tom's proved what I'm going to say for this non-stable Kuhn semigroup, this M infinity version. But then in a subsequent paper, Brown and Tom's did it for the stable version. All right. So the theorem is that if A is simple, unital, exact, and Z stable, unital, exact, and Z stable, then the Kuhn semigroup of A is isomorphic to, first of all, this Murray-von-Neumann semigroup. Okay. But by this notation, what I mean is supremum of increasing sequence of continuous numbers, continuous affine functions. Okay, so the Kuhn semigroup can be recovered, and in fact is equivalent to the Elliott invariant, except not for K1. So this recovers sort of K0 information and tracial information. There are certain ways of also trying to include K1 in this, but I won't get into. So I will expand on this more fully in a couple of weeks, but I'll just mention now so this is kind of the creme de la creme of classification results, what I'm going to tell you here. So this is due to Lionel Robert. And this is that CU classifies morphisms from one-dimensional non-commutative CW complexes that have no K1 to stable rank 1 algebras. The reason I'm calling this the creme de la creme of classification is because of how general it is. The codomain is anything of stable rank 1. What I mean by classifying morphisms is, let's say unital. From the way I described it, it also works in the non-unital case, but you need to replace CU by an adjustment. So what I mean is, if you give me a CU morphism from one of these guys to any stable rank 1, it is realized by a star homomorphism uniquely up to approximate unitary equivalence. I mean, this is incredibly powerful. And in particular, from this, you can deduce a classification of inductive limits of building blocks like this. So I will actually be using this very powerful tool of Lionel Robert when we get to some of the applications. Right. So I'll start there. Thank you very much.
Well, I must say that gravely pointed by 2 empty blackboards. Like having a meal without a dessert.
I owe you 2 next time.
Any immediate questions?
Yes, I have a question about the second part of this concept.
Yes.
Is this second part absorbing?
You mean, how am I defining?
I see some similarity between this decomposition and the decomposition of the case of C into N plus.
Yes, okay, I mean, I haven't really even told you what the addition or order structure is.
Yeah.
Yes, you.
Question also about this.
Yes, yeah. But no, but I don't think that's, yeah, maybe it is. Yeah, okay. Yes, to an extent, it's the answer. I would have to think more carefully about it. By the way, maybe I'll just mention quickly. So in particular, CU of the Jiangsu algebra is going to be extended naturals, union, the positive real line. That's what it is for the Jiangsu algebra. Or maybe I got the infinity in the wrong place, actually. It would be, no, sorry, I got the infinity in the wrong place. It's the naturals, union, the positive real line, including infinity. So yes, so the absorbing part, I think, does indeed live in this.
So in a sense, this first part is this coming from projections.
Yes.
And the second part, this absorbing part, it's this garbage.
That's how this map works. You take a positive element. If it's a projection, you map it here. Otherwise, you map it to this dimension function that you got here.
Yeah.
Good semi-group distinguishes Jiangsu from complex numbers.
Yeah, that's true. That is true.
Right, got it. Okay, let me stop recording.